Appendix E. Let me just zoom in a little bit. We're looking at sigma notation. All right, sigma notation. Let's see how things work here. Definition. They say if a subscript m, a subscript m plus 1, all the way up to a subscript n are real numbers, and we say m and n are integers, such that m is smaller than or equals to n, then this applies. So take note, this sigma notation here, this sign here stands for sum. It means summation. So summation from I equals to m all the way to n, all right, of a subscript I. What that simply means is my first term will be I is equals to m. So I go there, everywhere I see I here, I'm going to replace it with m. You see, I have a subscript m. Now my second term is I equals to m plus 1. You see, I have plus a subscript m plus 1, and so on all the way up to a subscript n. And please, because this goes all the way to n, it's a finite series. All right, I'm using the word series. So in general, we call this a sequence when you're separating each term by comma. And when there's a plus, we call this a series. So a series is just a sequence whose terms are being added. All right, so this is a series. So please make it good practice, right? If you have so many terms you need to write, because you can see there's infinite possibilities. There's so many possibilities, we can't really write them out. Please make sure when you use this 3 dot, which means and so on, include the second to the last term and the last term. Some people, they choose to include the third to the last term, the second to the last term, and the last term. All right, so include at least the 2 last terms, at least. All right, and we're going to see why that is important. All right, now let's see this easy examples. Let's look at the first 2. They ask you the sum from I equals to 1 to 4 of I squared. Obviously, if you see this in the test, you should be able to get it quick. It simply means that wherever you see I, just put 1. Second term is when I is 2. Third term, I is 3. Last term, remember this is your last term is 4. You just have 4 squared. And you add all of those, you just have 30. All right. Now, look at the second one. It's from I equals to 3 to n. Because you're not sure exactly how many terms are there, there have to be some n terms. You can list the first 3 or 4, and then you say plus, you put 3 dots, which means and so on. Then you say plus, and then include the second to the last term and the last term. Obviously, the last term is n. It means that the second to the last term is n minus 1. All right. I see no one has a question. It means everyone is happy. And that also applies to C, to D. It's just plug and play. But now I need to explain something is actually F. Now for F, don't get confused, guys. You have the sum from I equals to 1 to 4 of 2. If you notice it, this 2 is just a constant value. It's not associated with any I or J or K and so on. You see here, there's a K, and we going from K equals to 1 to n. Here there's a J, we're going from J equals to 0 to 5 and so on. But yeah, you just have a 2. It's just a constant value. There's no I, because we're starting from I equals to 1 to 4, but there's not 2 that associate with I. So there's no association between 2 and I. How does that work? It simply means that it doesn't have to change. You keep the constant as 2, and you just add it that number of times, all right? So when I equals to 1, you get 2. Plus, when I equals to 2, again, you just get 2 because it's a constant. And when I equals to 3, again, you get 2. When I equals to 4, you get 2, and you see you just have 8. It's as easy as that. In other words, it means add 2 4 times, all right? So you add the same 2 4 times. All right, let's do more examples. Example 2, they say write the sum in sigma notation. You see that there's so many possibilities, but these are some of the few answers that I'm expecting to see if I ask you this question. If I ask you to write sigma notation, remember sigma notation means I want to see the summation sign from I equals to something or from J equals to something. Okay, you can use any variable, all right? All right, so the first one is the easiest. You just say summation from I equals to 2 all the way to n. It's true, right? Because my first term there, I is 2. You see I have 2 cubed, which is fine because it's I cubed there. Second term is I, there will be 3. I have 3 cubed. You see it works. plus and so on. The last term you can see there's n. It's the one there at the top n. If you put n in there, you just have n cubed. You see this first one works. If you try the second one, again, it's going to work. It will give you this sum that you have there. And if you try this again, it's going to give you that sum. Like I said, these are not the only three. There's probably hundreds and millions of different possibilities. All right. In other words, I would just say the infinite possibilities. All right. Let's move to theorem. What does the theorem say? The theorem says that the sum, so if I take a constant c and I multiply it by sum, all right, so I have this a subscript item c. Now, because c there's a constant, you can take it outside of your sum, all right. For example, if I'm adding let's say 2 plus 4 plus 6 and so on, all right, everyone can already see that there's a pattern there. Each of these numbers, I can extract 2 from these numbers. So I can choose to say this is 2 times 1 plus 2 plus 3. All right. So that's the whole idea and so on. All right. That's the whole idea. So if you notice that there's a constant times each term in your sum, you can just take the constant out of your sum. All right. And similarly, if you have the sum of 2 different terms, so if you have a and bi, you can just split them out as well. So this is what we call the distribution rule as well. All right. So this is the sum rule, and this is the difference rule. All right. Now let's look at this. If you notice it, we've seen an example that looks like this, where you have a constant that is not associated with that I. All right. How do we do that? We say that we're going to go from I equals to 1 to n, and we just keep adding 7. In this case, n is not some finite number, all right? Meaning that we'll just keep adding 7 forever. We're going to have 7 plus 7 plus 7, and so on. And even when we hit n, it will still be 7. So in other words, we say add 7 n times, all right? I'll just do another example so that everyone is happy. Let's assume that I change that example and I say from I equals to 1 to let's say 10, all right, which is very long. And then I give you a constant value, the 10, all right. What it simply means is add 10 times, all right. So in this example, add 7 n times, all right. So it just becomes 7 times n. All right. If everyone is happy, let's keep going. Example 4 now is a proof. So let's see how the proof works. So we want to prove that this whole sum there, it simplifies to n into n plus 1 over 2. In my test, I would probably try not to ask you this proof. If I have to ask you this proof, it's going to be under something called mathematical induction. All right. So I might not want you to prove it this way. So I'll specify that use mathematical induction instead. But let's see how we can prove this without actually using proof by mathematical induction. We say let S stands for the sum. So S stands for this sum. All right. This sum that we're trying to prove. Let S stand for that sum. Now, there's 2 ways of writing this. So S will be equals to 1, 2, 3, all the way to, remember I told you always include at least the last 2 terms, which is n minus 1 and n. And S can also be written in the reverse order, all right? Because remember, A plus B, because I'm adding 2 things, the order does not matter here. So A plus B is the same as B plus A. So we say addition is commutative. Commutative means order does not matter. Means I can add going in this forward direction, or I can add them in the reverse, right? Going in that direction. So they are just write the same S in by adding in the reverse direction. So instead I start from n, n minus 1, all the way to 3, 2, and 1. All right. So these 2, they're exactly the same. All right. Just adding one in the forward direction, the other in the reverse direction. And if I add these two together, s plus s obviously is 2s. So I'm just pairing them. N plus 1, that's n plus 1. If you add the n plus 1 plus 2, so I pair these two them. Again, you see, it still gives me n plus 1. And so on. So if you keep pairing them together, if you look at the last term, it's also n plus 1. Second to the last term, if you pair this 2, notice it, you still get n plus 1. So there's a pattern there. So we say we're adding n plus 1 n times. Why n times? Look, it's there at the top. This is n. N is there at the top. N times. Whenever you start from I equals to 1, it means you have to add that number of times there at the top, which in this case is n. All right. So n times, what does that mean? It just means n times that repeating terms, which is n plus 1. So n times n plus 1. And if you make s the subject, you just have n into n plus 1 over 2. Easy. Now, this proof is fairly easy, but the other proofs may not be easy, right? For the next proof, which you need to pay attention, we're going to use something called telescopic sum, which there's a great probability you're going to see telescopic sum in your test or in your assignment. All right. Now, let's see how to use the telescopic sum, how it works. So I want you to prove this formula. All right. Please take note, we're not yet doing logics and proof by induction. So we want to use telescopic sum here. Now, to prove I squared, so to prove I squared, we're going to use the difference of cubes. All right. So these are unique values that you need to use this unique. So we're going to use the difference of cubes. And how does it work? We're going to write a telescopic sum. The word telescopic sum is that there is a pattern whenever you have this difference of cubes. All right. Let's see how the patterns actually comes about. First thing is, if I let I to be equals to 1, notice it. This first piece here just evaluate to 2 cube, and I cube is just 1 cube, you see. And then I say, okay, I group it. I call this my first bracket, and then I say plus, and I go to the second term. I equals to 2. I have this. I equals to 3, and so on. I use the second to the last term. Remember, second to the last term is n minus 1. So I equals to n minus 1. You get this, and then the last term is I equals to n. Now we call this telescopic sum. Why? Look at the pattern now. You notice that this first term here, 2 to the power 3, it looks like something here as well. So you see, it cancels out because 1 is positive and 1 is negative. All right. So your first entry for your first term, so if we're treating this bracket as each term, the first entry here cancels with the second entry in for I equals to 2. All right. And the pattern keeps going. The first entry now in the second bracket cancels with the second entry in the third bracket. Similarly, this first entry will also cancel with some second entry in the next term. All right. And you notice that the only guy that is untouched is this guy, minus 1 cube. It's completely untouched. All right. And then if we look here towards the end, the first entry, which is n cube, cancels with the second entry in the next bracket. You see, it goes away. Because this is a second entry, you know it is going to cancel with the first entry for the term that comes before this term here, this whole term here, right? Now, because n plus 1 cube is the first entry of my last term, there's no other second entry going that direction, right? Because we're done, all right? There's no other term. It means it's also untouched. So notice it. This guy is untouched, n plus 1 cube, and as well as your minus 1 to the power 3. They're the only ones that didn't have any partner to cancel out with. All right. When I say cancel out, it's real cancellation, guys. It's not that you just find matching terms and you cancel them. 2 to the power 3 cancels with this term because of this minus sign. You see, there's a minus sign in front. If you pair them together, they disappear. That's why I'm canceling them. Terms don't just cancel out if they're all positive. One has to be positive, the other has to be negative. Guys, that's what we call telescopic sum. All right. And if you simplify this, so if you say n plus 1 cube, if you expand, obviously minus 1 cube is just minus 1. If you do that expanding, you get n cubed plus 3n squared plus 3n. All right, that's your first equation. So if you have to prove this, you've gotten some good marks already. Another way of simplifying this whole thing here, another way of simplifying this is by using what we know already. So 1 plus I cubed minus I cubed. So if you expand this and you simplify, you end up with something like this: 3I squared plus 3I plus 1. And if you remember well, the distribution rule says that I can take this sum, so I can take sum of each of these terms separately. So I have 3 times the sum of I squared. For the second one, you have 3 times the sum of I, and it's just 1 there, so it'll just be the sum of a constant term, which is 1. All right. Now, let's see how it works. You have summation from I equals to 1 to n of I squared. If you remember, that is what we're trying to prove in the first place, all right? And we call that S. We say let S be the sum, the desired sum. So 3 times this just means 3 times S, because that's what we're trying to prove in the first place. We've already proven this. If you remember, the first proof we did was the sum from I equals to 1 to n of I, which we concluded that it was n into n plus 1 over 2, all right? And what is the sum of from I equals to 1 to n of 1? It means at 1, n times, which is just 1 times n, right? It's n. There we go. So if you simplify this whole thing, you end up with 3s plus 3 over 2n squared plus 5 over 2n. And you call that equation 2. So I just simplified this whole thing, right? I multiplied everything out here. Now, these two equations have to be the same because it's just me expressing these two things in different ways. The first way I use telescopic sum. The second way I'm just expanding and using my identities. All right. If this 2 has to be the same, I say bet 1 has to be the same as 2. It means that you can equate this guy equation 1 to equation 2. And the focus there is S. We want to make S the subject. So you take 3S, you leave it on one side. You take everything S to the other side. You end up with this whole thing. And if you divide all 2 by 3, there you go. You can choose to factor out. If you notice it here, n is common. So we can factor out an n, and you end up with the final answer, which is just n into n plus 1 into 2n plus 1 over 6. There you go. You have proven it, all right? Because there's a proof that I wanted you to show, all right? So there's a proof, this proof here, all right? So you've shown that this guy equals to that. But like I told you, you had to use something called telescopic sum. We're going to see again where telescopic sum is useful, all right? It's very useful. I'm telling you in advance because you're going to see it somewhere in the future in the test. Okay, another term. So there I say remember means that, guys, this thing say you need to remember them because we working from home. You're more than welcome to quickly look at your notes. Please don't write the wrong formula in my test because it's open book test basically. So this is important. Please, if I ask you something, let's say you see this somewhere, just remember that it equates to this. All right. So 1 is just n. C is just n times c. I, we've already proven this. We just proved I squared. I didn't show you guys a proof for I cubed, but you can see that I cubed just looks like the square of this. This is this whole term or square. All right.